In this lecture, we're going to look at primes factorization. What is primes factorization? It's this procedure of writing an integer n into a product of primes. It turns out for any positive integer n, there's a unique way of writing this n into a product of primes. And this procedure is known as the prime factorization. So prime factorization is basically factoring a positive integer n into primes. So for example, 6 can be written into 2 times 3. And 2 times 3 is a prime factorization. 9 equals 3 times 3. It's a prime factorization. And 12 equals 2 times 2 times 3. 16 equals 2 times 8. Now this is not a prime factorization yet, not the final form yet, because 8 is 2 times 2 times 2. And this is prime factorization. So this lecture is going to focus on how we do the prime factorization. Now, prime factorization is actually, turns out, it's just very, very mechanical. And that's really good for computers. But unfortunately, we cannot really bring a computer into math contest or most of the math exams. And anyhow, we also need to understand if the computer does something, we need to understand how it does it. What's the rationale there? What's the method it's carrying out? So we want to understand how we do prime factorization. Now, prime factorization is really nothing but a recursive algorithm. So instead of talking about abstractly, now instead of talking in an abstract way, let's just focus on one concrete example of a number, and let's see how we do prime factorization. Let's focus on an integer, let's say 72. To do prime factorization, it's a recursive way. First, let's find out what is the smallest prime factor of 72. And then we divide 72 by that smallest prime factor. 72, the smallest prime factor is 2. And here I'm going to represent the prime factorization using a tree structure. So it has a 2 prime factor, and then 72 divided by 2, in here I'm writing 72 divided by 2, is a 36. Now we just do this determination. Is 36 a prime number already? No, because 32 still has other prime factors. If this is not a prime number, we keep doing this. Okay, so we have a 2 already, and we just do the prime factorization of 36. For 36, the smallest prime factor of 36 is a 2. And in this branch of the tree, I'm going to write 36 divided by 2. It's 18. Now, since 18 is not prime yet, we keep doing this. Now doing this new step on 18. The smallest prime factor for 18 is again a 2, and then left with a 9. This number, again, remember this is 18 divided by 2. So for this 9, because 9 is not a prime number, we find out the smallest prime factor for 9 is a 3. So put a 3 here, and this is a 3. Now since 3 is a prime number, we are finished, we are done. And this is called the prime factorization tree. And what's the final form of its prime factors? We're going to collect all the branch leaves, it's so-called the leaves, on the edges of those things. And these are the leaves. And we write down 72 as the product of its leaves. 2 times 2 times 2 times 3 and times 3. And clearly by the way that how we construct a tree, you know that must be true. That 72 is going to equal 2 times 2 times 2 times 3 times 3, because you just think about reversely. 3 times 3 equals 9, and 2 times 9 equals 18. 2 times 18 equals 36. 2 times 36 equals 72. And this is exactly the product of its leaves. So 72 equals 2 times 2 times 2 times 3 times 3. And this is the prime factorization. Some people prefer to write in a divided way. Similarly, a divided way is useful in later if we want to calculate the greatest common factor of two numbers, because in there you can using a similar form of this structure, dividing. So first you find the smallest prime factor of 72, 2, and 72 divided by 2 is a 36. And again, there's the smallest prime factor of 36 is 2, and this in here is just 36 divided by 2 equals 18. And just 18 divided by 2 is 9, and the smallest factor, prime factor of 9 is 3, and it's 3. So this, apparently these two are really like, it's just a different form of representation. It's exactly doing the same thing. And again, the 72 will equal the product of all those numbers outside of this structure. It looks like L. So 72 equals 2 times 2 times 3 times 2 times 3 times 3. Now this is prime factorization. Except here, we're going to collect all those same prime numbers together so that we have a more compact way of writing it. And we have not really learned that, but I'm going to define 2 times 2 times 2. I'm using a form called a power form, or a base with exponent. 2 to the power 3 and times 3 to the power square. Now, this power, let's say 2 to the power 3, it's defined as you have 3 2's multiplied together. So 2 is the number multiplied together, and this 3 is how many times are multiplied together. Okay, so this is known as the base, and this is known as the exponent. So I'm going to define more generally. A to the power n is defined as a times a times a times a n times. Now apparently n here is, I'm thinking n as a positive integer. And later we'll know that this power form can be defined for decimals, fractions, does not really matter, negative numbers, we all can define that way. But we have to do a bit of an extension of this. But if we start with, we think about n as a positive integer, and we can define a to the power n equals a times a times a, n a's multiplied together, and this is called the power. Exponent, number powers, base and exponent. So now you can collect these things in the power form. 2 times 2 times 2 equals 2 to the power 3 times 3 squared, because there are two 3's multiplied together. And this is the prime factorization. And if you order the primes from the smallest to the largest, then this prime factorization is unique. And this is a fundamental theorem. The prime factorization theorem says, well, actually rather it's more of a definition. For any number n, you can prime factor n into a product of primes with exponents. So for n, it can be written as p1 to the power a1, p2 to the power a2, pk to the power ak. And this process of writing into this form is called the prime factorization. And this form, if you order those pi's into increasing order, so start with the smallest and increasing, p1 less than p2 less than pk, then this form is unique. And this is so-called unique prime factorization result. And this is going to be super useful as we understand the property of this number n. We talk about what numbers makes a number m, or m is a divisor of n, we can look through the lens of prime factorization. What numbers is a factor of both m and n, or what is the GCF of m and n? We can look at that through the lens of prime factorization. What is the least common multiple of m and n? Again, we can look at that through the lens of prime factorization. And how many factors n has? Again, we can use prime factorization to derive a very, very important and very easy result about the number of factors of n. So this prime factorization is extremely important result. And we're going to talk about all those we can use in prime factorization to derive in later lectures.